Hello viewers, these are key messages from the Ministry of Basic and Secondary Education on the coronavirus. Dear parents, keep children at home at all times. Avoid sending children to shops and markets. Do not engage children in petty trading on the streets and garages. Allow children to play within the confines of the home. Limit visitors into your homes. Adhere to COVID-19 health precautions and guidelines. Schools are closed, but learning continues. Dear teachers, you are encouraged to desist from all forms of group activities involving students. All school premises should remain closed and not to be used for any other purpose. Thank you.
Good day viewers and welcome back to my physics class. This is part 2 of alternating current, and in this chapter or in this video we'll be dealing with definition of reactance in general, reactance denoted as X, and that of the impedance in bracket Z. We will also deal with the combination of RC circuits, the combination of AC circuits, and the first on the list will be RC, combination of resistor and capacitor circuit, followed by RL combination, and finally to RLC combination and resonance. Good. So I will need you to recap or to take your previous lesson as a review, and then so that we will flow easily without any problems in what is to be done today. Good. Now the first thing we will talk about here will be the reactance. Like I said previously, the reactance refers to the opposition which an inductor or a capacitor offers to the flow of alternating current. It is measured in ohms and it is represented as X. But then if you see something like X sub C, you should know that that reactance is referred to the reactance in the capacitive or in the capacitor circuit, and X sub L will be the reactance offered to the opposition of flow of current in the inductive or inductance circuit. Is that understood? But when all these are combined together, all these oppositions are combined together in a circuit or in an AC circuit, the result is what we call impedance, and it is denoted as Z, and then its unit is also ohms. Is that understood? Good. The first one is RC circuit. The circuit has to be drawn, and we have the combination of resistor and capacitor in this circuit. We have to indicate the presence of R and that of C, the voltage across V and the voltage VR across the capacitor, and voltage VC across the capacitor. All you need to know that is that all of these components are combined in a series arrangement, and that tells us that the current I the current I is the same. Since the components are arranged in a series arrangement, good, the total voltage is not equivalent to VC, and it is also not equivalent to VR. Is that understood? But like I said, when you're dealing with alternating current, after looking at your diagram, the first or second thing you do is to draw a phase diagram. And I told you what a phase diagram is. It is a vector diagram which shows the magnitude and direction of the voltage and current. Now when we have the components combined, their phase diagrams will be drawn in terms of their voltages or in terms of their reactance. Their reactance. Is that understood? But then the rule stays the same. All you need to do is to connect. How was the voltage, directed when we dealt with a pure resistor, and how was it directed when we dealt with a pure, capacitor separately? Then you combine those two to form a phase diagram of R and C combined in a single circuit. Is that understood? You will recall that the phasor diagram for that of a pure resistor was something like I here and V here. But then as I said, the voltage here, the phasor diagram will be in terms of voltage. So I wouldn't be captured. So we are going to draw the phasor diagram of these two in terms of their voltages. But then you recall that the voltage of a pure resistor was horizontal and the voltage of a pure capacitor was vertically down. This is VR and this is VC. That was because voltage was lagging behind the current in a pure capacitor circuit, and then current and voltage were in phase for a pure resistor circuit. Is that understood? So we are just omitting the current, taking note of their voltages. And this gives us the angle at which the two are inclined, and that angle is known as their phase difference. Is that understood? Good. But then since I said a phase diagram is just a vector diagram, we can complete this using a parallelogram, and that should be something like this. And you know what the law of parallelogram states? The diagonal, the main diagonal, will represent the voltage, or the total, or that will represent the voltage, that will represent the resultant voltage. Is that understood? And that should be V. So in essence, we know this is the diagram we drew. It can be rotated to obtain something like this. This is VR and this will be VC. Note the arrowhead. The arrowhead tells us that VC is lagging behind, and that's the resultant voltage V, and this is the angle or the phase difference between the two. Is that understood? Good. Now we can use the vector, we can use parallelogram's law of vector addition to obtain VRs, V squared. You will notice that this length here is equivalent to this side. And if this is completed, we will obtain VC here will be the same VC here. So you extract any of this triangle. If one is extracted, something like this, the one which is enclosed at 5, we will have VC and VR, and this will be the magnitude of V. Understood? Good. So this is the phase diagram in terms of voltage. And then we can solve for V. We know V squared is equivalent to VR squared, that's Pythagoras theorem, plus VC squared. But again, if you recall from last class, we were told that VR is equivalent to I times R, and VC is equivalent to I times XC. But then the components are also arranged in a series, and that means I is just common. That is why I didn't give the current any initial. Is that understood? So substituting this into the equation will give us V squared is equivalent to IR all squared plus IXC all squared. You will notice that I is common, or I squared is common. If you simplify, this becomes I squared R squared plus I squared XC squared all equals to V squared. Can we make V the subject? Yes, and that is done by taking the square root on both sides, and this will be V equals to, the root will cancel that 2, this will be the root of I squared into, since I squared is common, we can factor it out, and that will be I squared into R squared plus XC squared. And the root of I squared will be I. So V, that is the effective voltage, will be I, or let me just simplify it because of the slow learners I have here. The root of I squared times the root of R squared plus XC squared. And this will be, V is equivalent to, the root of I squared is simply I times the root of R squared plus XC squared. That is the effective voltage. That is the effective voltage in an RC circuit. Clear? Good. But again, we want to know the effective opposition, which we call Z. That is the impedance. V is just the same as the voltage. So it is just the same as the total resistor. Good. So this gives us V equals to I into the root of R squared plus XC squared. If we divide both sides by I, we will have something like V over I is equivalent to the root of R squared plus XC all squared. But then from Ohm's law, V over I gives us R. And R is just the resistor, the resistance, which is the opposition to the flow of current. But then in this case, the opposition to the flow of current is known as Z. So V over I is simply written as Z, which is equivalent to the root of R squared plus XC squared. So the impedance in a RC circuit combination will be Z equals to the root of R squared plus XC squared, where R equivalent to the opposition to the, that's just the resistance. Let me define the terms for you. Z equivalent to the impedance, and the unit must be ohms. R is also the resistance, and the unit must be in ohms. And XC is the capacitive reactance, the capacitive reactance, which is also measured in ohms. These were all defined terms, and then that's all for this particular diagram.